Hi there. Thank you for being here today. My name is Rory Telemico, and I'm really excited to tell you about some of the work that my lab and I have been doing over the last few years to help inform conservation and eventual repatriation of blunt-nosed leopard lizards in the Panoche Hills in western Fresno County, California. One of the big things my lab has been trying to do is really understand what are the requirements for all stages of blunt-nosed leopard lizard to persist, survive, do the things they need to do, and how will each of these life stages affect the population growth trajectories for the population. And as you're probably aware, there are both phases of the life history of these animals in most species that are pretty easy to get at, and phases that are much harder to get the data for, just because the animals are cryptic during those phases, or because there's real risk of damaging the animals during those phases. So this figure shows the blunt-nosed leopard lizard life cycle. These animals, they're born as eggs. Those eggs are generally placed in a nest in the ground, although so far, no one has actually observed that I'm aware of a natural nest from blunt-nosed leopard lizards. The eggs I'm showing here are actually from the captive colony at Fresno Chaffee Zoo. After about 1 to 2 months in the ground, these are going to hatch out as young little hatchlings. Those hatchlings will emerge. They're going to forage in the late fall, try to get enough energy reserves that they can go underground and survive their first hibernation underground. They will emerge in spring as yearlings. They may or may not be reproductive yet, depending on quite how big they got in the fall. If they're already reproductive, they can just start going. Otherwise, they're going to keep growing for a few weeks, then become reproductive, and they can start reproducing. If they survive that first season, they're then going to go underground and hibernate again. If they survive that, come back up as a 2-year-plus full adult blunt-nosed leopard lizard. Now, of all these life history stages, the ones that we've got pretty good data for are shown here and highlighted in green. And they're those stages when the animals are above ground and fairly easily accessible. However, to really understand and manage the species, we need to have a good sense of what's necessary for all the life stages, as well as a good sense for the probability of making it from one stage to the next. So really attaching numbers to every one of those arrows. For the rest of today, I'm going to be talking about the work we've been doing, in particular trying to fill in a handful of these arrows focused on reproductive output and reproductive success, because those early life history stages typically are some of the most sensitive, and for blunt-nosed leopard lizards, they're what we have some of the least data for. So we were really needing to figure out how many eggs do females produce naturally? What is that reproductive output? Does that differ between yearlings and older females? And then what are natural incubation conditions? What conditions within the nest actually will allow eggs to hatch and produce high-quality offspring? The incubation conditions within reptile nests have a very large effect on fitness-relevant phenotypes in these animals. It can do everything from determine whether or not they hatch, but then also affect their post-hatching growth rates, the relative body shapes. It can affect their relative colors. And in some of the most extreme cases, it can actually affect whether they hatch out as males or females. Although that does not seem to be the case in blunt-nosed leopard lizards, and temperature-dependent sex determination is not actually documented for any North American lizard, or really the families that contain the North American lizards. But even so, we need to know what are conditions that will allow eggs to hatch out well and produce good offspring. And that's where we're going to start. And really doing this means we're focusing in on the arrows and the box shown here. We're trying to figure out what is that reproductive output, how many eggs are being produced, and how many of those are hatching. So to get at how many eggs are being produced and how that egg development is occurring, we implemented field ultrasound. The device we used is pictured here on the right, and you can see one of my students, Catherine Ramirez, and myself performing an ultrasound exam on a blunt-nosed leopard lizard in our field tent there on the left. This ultrasound is the same quality as a medical ultrasound that you would see in a hospital. They're about the size of a medium to large laptop. They're a bit thicker, and we're able to detect quite well egg development within the females. An example of that is shown here. On the left is a still image showing 2 early stage follicles. These are still within the ovary. One of them is circled by those green dots. And then on the right, I'm showing you some later stage oviductal eggs in the oviduct. And that's in this movie to the right. So you can see those 2 large kind of grapes that are coming in and out of focus. Those are the 2 eggs. And we're able to detect the eggs before you could feel them by palping, and we're able to count them reliably even when they're either too small to feel or have gotten so big that they can be hard to really distinguish one from the other within the female's body, allowing us to get a much better sort of count of the reproductive output. We're also able to measure these eggs and get a sense of how the developmental trajectory is progressing in utero for these females and about how long that takes. And we can detect anomalies. So for example, this is an image on the left and video on the right of a female who is egg-bound. We detected that she still had an egg in her body well into August. And when we gave her an ultrasound exam, we could see a well-developed embryo inside that egg. So on the left, the head is sort of down to the center of that wheel, and then its body curves around, and that's a well-developed, probably dead embryo within the body of this female. And when we bring all the data together, we were able to reliably count the number of clutches that are being produced per season. So we can actually tell this quite well, not just based on if we feel the eggs disappear and then we feel an animal with eggs again, but we can tell based on the stage they were at how likely it is that we're now seeing a new stage than one we saw before, or we're still seeing the same clutch of eggs. So with this, we discovered that 1 clutch was the most common, but honestly, it seemed like 2 is what they were after, because the only females to produce 1 clutch are those that either started late in the season or those that died or went missing before they could produce the second. If they were old enough to start reproducing at the start of the season and didn't die, they basically always produced 2 clutches. And we did see 1 case of a female producing 3 clutches in the field. At the zoo colony, the females there produced 3 clutches in the first season we had them at the zoo. So it does seem they can facultatively produce 3 clutches if conditions are really good, are generally kind of aiming for 2 clutches, but 1 is sort of writ large the most likely to happen. We also found that these females almost always produce 4 egg clutches, 2 eggs from each ovary per clutch. We one time detected a 5th egg in a clutch, and a few times we detected smaller clutches, but again, those smaller clutches seem to be a result of damage, like an ovary was damaged and not working. Additionally, we never saw signs of overlap in clutch production. We never saw a new follicle starting to ripen until the earlier eggs were actually oviposited into the substrate. And because of that, we were able to use our second clutches in particular to estimate how the size of the eggs varies across in utero egg production. Because we could know when a female laid her first clutch was the start date of her second clutch, and then do number of days from then to get our days of development. These data are shown on the plot here. The x-axis is days of development. The y-axis is egg volume, measured again via ultrasound within the body of the female. And then that vertical solid line is the average interclutch interval that we've observed from the zoo colony. We then fit a linear regression to the data. We tried multiple model shapes, but the linear regression fits the data best and is preferred given the data that we currently have. And this line model explains about 60% of the variation in egg volume data that we were able to estimate. So that's the work we've done to just get a sense of what is the potential reproductive output by these females in the field, and how is that varying across the life stages. But another thing we really need to know is what are the conditions within those natural nests? Because the conditions within those nests are going to be determining what the final phenotype of the hatchlings are, and we would generally expect that the sensitivities of the eggs have evolved, been under selection to sort of match the conditions most typical in the environment. So our expectation would be those natural conditions should produce some of the best quality offspring. So that's something we want to know so that we can both recreate it in captivity, but also look for those conditions on the landscape that are going to best allow females to nest. Now, unfortunately, as I mentioned, no one's observed one of these nests before, so there's no data in the literature about exactly what it's going to take to incubate a blunt-nosed leopard lizard, or what a natural condition might be. And digging up the eggs has some risk. It could possibly damage the environment. It could possibly damage the eggs. So we turned to modeling. In particular, we turned to Niche Mapper. This is a microclimate modeling framework. It started development in the 1970s by Warren Porter and colleagues. It was initially developed in Fortran, has now just continued development and getting better and better, and it's now freely available through R via the Niche Map R package. And what it does is it uses high-resolution climate data, publicly available climate data. It then uses physical principles and some statistical downscaling to take broad-scale meteorological data that's generally collected by weather stations and really convert that into the very fine-scale inputs that are going to influence the body temperature and energy balance of an organism on the landscape. So like air temperature at 3 meters basically isn't meaningful for an animal on the landscape, but soil temperature on the soil surface is. So is how much solar radiation is going to be hitting an animal right there. Those are the things that are directly determining the body temperature and energy balance of an animal. And that's what's output by the first main module of Niche Map R. It also has subsequent modules where you can use those as inputs to actually calculate the body temperatures hourly for these animals at any time and place, really on the globe, although it's been very well validated for the continental US and has not been so well validated many other places. So this is what I used to estimate what conditions might be available to a female leopard lizard on the landscape in the Pinochet Plateau. To give you a sense of the kind of outputs you can get from this, this figure shows modeling work I did just estimating the temperatures that an egg would be exposed to if a female placed that egg either in full sun, the column on the right, or under 90% shade. I'm sorry, the sun is in the column on the left, shade is the column on the right. And as you go down, I'm varying depth. So the very most shallow is 10 centimeters below ground, approximately 6 inches, and the deepest is a meter below ground. Now, I modeled these because this is the choices that females really have, the control they have for where they place their eggs. On the panoche, there's really just scattered ephedra and full sun, bare ground. So their choice is going to be to nest under one of those ephedra or under the bare ground, and then they can choose how deep to lay their eggs. Although typically related lizards are going to be laying their eggs around 6 inches below ground or 10 centimeters. So that's generally what we went with when we were trying to model the conditions that we're trying to model the conditions that eggs would experience. However, ideally we would have some real observations and know exactly what the females are doing and what the females are choosing. But this is a great given that we don't have that yet. Using this modeling approach, I modeled out the soil temperatures over the 10-year period in the Panoche Plateau. And I used a 10-year period from 2006 to 2015 because that's before we think the population started to decline. These were hourly temperature data, and I generated them for that 10 centimeters below the soil surface, and then averaged those out across that entire 10-year period to work out what is the average daily temperature cycle that natural eggs would expect to experience on the Panoche Plateau, and that is shown by the figure on the right. This is the daily cycle that we would expect eggs in nature to be exposed to, and so this is what we use cycling temperature incubators to recreate when incubating animals for a captive colony at Fresno Chaffee Zoo. The majority of eggs hatched. We got 19 successful hatchlings. Those hatchlings are doing quite well in captivity still. So this seems to have worked quite well to give us a evidence-based incubation strategy for these eggs in a way that should produce the best quality hatchlings we could get. But this really is just scratching the surface of what you can do with this tool. You can explore really any variation in the microclimate you might want that you have a reason to look at because it might influence your organism of interest. So for example, this plot shows water potential variation in those same nests that I modeled temperature for on the Panoche Plateau. This is again at 10 centimeters depth. And now instead of just averaging the average line over that period, I'm showing you the variation between years, and they're separated by color. If you're unfamiliar, water potential is the force behind osmosis. And everything has a water potential, or everything with solutes in it does. And the more negative the value, the drier that substrate, the harder it's holding on to water. And this is basically like a tug of war. Whichever side is pulling harder will end up with the water. So if the egg has a more negative water potential, it draws water into itself. If the soil has a more negative water potential, it draws the water out of the egg, will dry it out and kill it. Now the gray shaded region on this plot shows the range of water potentials that reptile eggs have successfully been hatched within. And that darker gray region shows the range of water potentials that reptile eggs, particularly lizard eggs, tend to do well in. This is where we incubate eggs in the laboratory if we want to make sure we get hatchlings. And what I think you can notice here is by July, by like the second week of July, and every year, water potentials were so dry, so negative as to be well below what is viable for most reptile eggs. And this suggests that either blunt-nosed leopard lizards have a very cool adaptation that allows them to deal with this dryness where most other reptiles can't. Or, and more likely, this is just a real limit to their reproduction at this site. And it means that if eggs are still in the ground by mid-July and haven't hatched yet, they probably are not going to, meaning that those later clutches that females might be producing are not very likely to survive. And this is something that we're planning to look into more in the coming seasons. So the big take-homes. We really need information across all life stages, not just the easily accessible life stages, to make real evidence-based management decisions. We've been implementing 2 such methods, field ultrasound and microclimate modeling, to what seems to be quite good effect. With the ultrasounds, we've been able to really quantify reproductive output by the females, eggs going onto the ground. By comparing that to hatching success, we're able to get a sense by number of hatchings, we're even able to get a sense of hatching success, really helpfully helping us figure out 2 of those important transition probabilities for the full life cycle. And the niche mapper allowed us to generate a naturalistic incubation profile for our eggs in our captive breeding project, even though we didn't have a single data point for a natural blunt-nosed leopard lizard nest. And it also allowed us to see that water potential is probably a very limiting factor for these eggs, probably more limiting than temperature, and therefore it's giving us direction to try to then begin to examine more carefully in the field. So thank you all for your time. I really appreciate it. I also need to thank the very many people that helped out with this work. It definitely was not mine alone. I've had a couple generations of the lab already move through working with these animals, shown by these pictures. Also lots of help from colleagues and co-authors with the zoo and BLM. And then our funding came from Fresno State University, Fresno Chaffee Zoo, and the BLM. With that, I'm excited to take any questions you might have. You put them here in the chat, or hopefully I will see you in person in Reno. Thank you, everybody.